All right, let's just jump right in. Today, we're diving into a seriously fascinating publication from OpenAI that dropped on June 17th, 2026. And look, this isn't just another story about an AI model passing some standardized test or writing a poem. This is about AI physically stepping into a laboratory. Quick heads up before we really get going, this explainer is strictly for educational purposes, so definitely don't take this as financial advice. Okay, let's unpack exactly what OpenAI and Molecule.one just pulled off. I want you to focus on this number for a second, 10,080. When we usually talk about AI and science, we're picturing chatbots summarizing research papers, right? But this explainer is all about real, measurable, physical output in an actual lab workflow. We're talking vials, complex instruments, real chemistry. That number is the sheer volume of actual reactions run for this project. It totally shifts the conversation away from AI hype and directly into physical research throughput. And that brings us to the big, overarching claim straight out of the OpenAI source card. They state, a near-autonomous AI chemist improves a challenging reaction in medicinal chemistry. Now, the absolutely crucial phrase here is near-autonomous. We aren't talking about some humanoid robot replacing a scientist in a dark, empty room. We're talking about a frontier model, specifically GPT 5.4, actually being wired into an experimental loop to optimize real-world molecules. Section 1, breaking down the workflow. So, to truly grasp the magnitude of this, we really need to look under the hood and understand the strict boundaries of how this worked. It's a three-step dance. First up, the model did the heavy reasoning. GPT 5.4 generated and ranked the research proposals. Second, those plans were handed off to Molecule.one's Maria AI, which translated them into instructions for an automated lab to execute thousands of times. And third, and this is key, human chemists were the essential final step. They had to review the automated work and actually repeat the critical reactions by hand to validate them. The timeline here is super helpful because it brilliantly illustrates that this was not some instant chat completion that took 3 seconds. The workflow kicked off on March 4th, 2026. The physical lab runs and the human validation kept grinding along until June 4th, and then the research finally published on June 17th. This was a grounded, months-long physical process that completely integrated AI reasoning with hard physical lab work. But wait a minute, let me put my skeptic hat on for just a second. Looking at this highly structured setup, we've got to ask, is this true scientific leverage? Or is it just a carefully staged frontier model demo meant to look like autonomy? Are we actually seeing a massive leap forward here? Or is it just a really, really good marketing campaign? To answer that skepticism, we just have to look at what happened in between those steps. Humans still had to select the final proposals out of whatever the AI generated. Humans stepped in to correct experimental plans when things got weird. So a total human replacement? Actually, scratch that. It is absolutely not a human replacement. The most accurate framing here is that this is a near-autonomous workflow. It gives scientists massive leverage by handling the grueling work of proposal generation and high-throughput execution. But the humans are still flying the plane. Section 2. The yield improvement numbers. Okay, now that we've established exactly how the system worked, let's get into the hard data. GPT 5.4 and Maria targeted something called Chan-Lam coupling. In plain English, it's a notoriously stubborn reaction used to stick molecules together to build drugs. The AI proposed using mild oxidants, specifically one called tempo, to try and force the reaction to work better. This grounds the whole experiment in a highly practical, incredibly real-world medicinal chemistry challenge. And the results? Honestly, they're striking. Under AI-optimized conditions, chemical yields improved for 88% of the tested boronic acids and 83% for sulfonamides. Hitting an 88% improvement rate across the board, that proves this wasn't just a lucky fluke. The AI's proposal worked consistently across a really broad set of physical tests. Let's look at how that actually shifted the baseline. The starting mean yield across the board was just 16.6%. But under the AI's optimized conditions, that mean yield jumped to 25.2%. Now, in the daily grind of chemistry, optimizing a stubborn reaction so it consistently produces significantly more of your target compound, that is a massive operational win. But, mean yield isn't everything. Usability is what actually matters at the end of the day. Look at the surge in reactions crossing the critical 30% usability threshold. Before the optimization, only 15.6% of the reactions hit that mark. after the AI workflow stepped in, a staggering 37.5% crossed it. What that means is chemists are throwing away far fewer combinations, and they have more than double the amount of usable pathways to work with. And importantly, these automated findings weren't just trusted blindly. Human chemists took the AI's best results and validated them entirely by hand at the bench scale. And guess what? They found higher yields for 11 out of 14 substrate pairs they tested. This completely validates the whole automated loop. The machine found the optimization, and human hands proved that the chemistry held up in a traditional, everyday lab setting. Section 3. Impact on research economics. So, the science is solid, but let's shift our focus from the lab bench to the boardroom for a minute. We are witnessing a fundamental shift in research economics here. For a long time, we've kind of viewed AI as a brainstorming buddy, right? Something to summarize dense papers or generate a quick list of ideas. But what this explainer shows is AI acting as a relentless R&D throughput engine. It's physically compressing the time and the cost between formulating a hypothesis and getting a physically validated result. And let me tell you, that is where real value is created in biotech.
But let's pause and ask the hard question. We have seen one highly impressive, very successful Chan-Lam coupling optimization. So, does one successful reaction justify a massive shift in biotech capital? Should we completely overhaul how we budget for R&D based on this? Isn't it just a bit premature to declare a total revolution?
Section 4. Risks and missing data. Honestly, that skepticism is completely valid, and it absolutely deserves a grounded reality check. We have to remember there are some critical missing variables in the public source set. First, unproven generalization. We don't know if this works just as well on totally different unrelated reaction classes. Second, missing cost data. OpenAI hasn't actually priced this improvement against what a conventional, human-only chemistry team would cost. Third, we're still waiting on independent outside replication. And finally, remember that this entire system was still heavily reliant on specialized infrastructure and expert human steering to even function. Section 5. Operator checklist and verdict. So, if you're out there navigating these endless AI headlines, how do you separate the actual signal from all the noise? Well, here is a concrete 4-question filter you can use. Ask yourself, 1. What exact workflow did the model touch? 2. What was the physically measured gain? 3. What was the human validation step? And 4. What is the unanswered cost question? If a headline can't answer those 4 things, it's probably just impressive branding. But if it can, like this study we just looked at, then it's true leverage. Ultimately, what these 10,080 lab runs actually prove is that we have an early but incredibly real R&D leverage signal. It is firmly not proof of autonomous scientific replacement from end to end. AI isn't going to just fire the whole chemistry department tomorrow. No way. But it is creating highly measurable, incredibly valuable throughput right at that tricky intersection where research hypotheses meet physical execution. Which leaves us with one final thought to ponder. As this technology matures and these models get even more integrated with physical robotics, where do you think AI will change research economics first? Is it going to be purely in generating the initial hypothesis, designing the experiment, or, like we saw today, dramatically scaling up the raw lab throughput? Thanks so much for joining me for this explainer, and keep asking the hard questions.